us about superconductivity and loop currents from cuprates to Kagome metals.
Yes, thanks, Paula. And yeah, once again, thanks to the organizers for putting together this marvelous meeting. It's been absolutely wonderful so far. We don't need an additional introduction after yesterday's excursion, what Kagome materials are. They are on display in Sao Paulo, if you pay attention. And the best part is, I don't know whether you saw this guy, but he was pretty awesome, playing right in front. Huh? Oh, sorry about this. He was horrible because of the wrong shirt, but otherwise pretty awesome. Okay, and oh, I can see here, but I cannot see where my pointer is. Good. So this work on loop currents was done primarily by two wonderful young researchers, Daniel Schulz, who is a postdoc in Karlsruhe, and Grugo Pala, who is a postdoc in Illinois. Risto Järvi is now back in Finland, was involved in an earlier part of this project, and we had absolutely wonderful interaction with Yongbek Kim in Toronto and with Raphael. Good. So when we look at ordered states that are not affected by spin degrees of freedom, what comes to mind maybe as a most straightforward state of order is when you accumulate a little more charge on one lattice site or in one orbital and a little less elsewhere. A next level of the abstraction that is actually more relevant to the materials we wish to discuss, in particular the Kagomes, is if you change the strength of a bond in one direction compared to another direction. Both of these two states preserve time reversal. And then there's a charge state that is often referred to as a loop current state, where indeed we have locally loops of currents that flow around. And obviously, once you reverse the direction of time, these arrows here change their direction, and hence the state changes its character. The accumulated flux in this little square here changes its sign, and time reversal symmetry is non-trivially affected. So this is an odd under time reversal state. This is what we will be discussing in this talk for a number of cases where we want to see what is the impact of such loop currents and their fluctuations on the emergence of superconductivity. So just to get slowly familiarized with this, if I take the charge in a given orbital or in a given site, and all I do is I evaluate the commutator of the charge with the typically kinetic energy or the entire Hamiltonian, depending on what system you're looking at, that gives you bond currents where you go from the given site to all other possible sites. For a system where this is just a hopping non-locality, you find bond currents given by this expression, the discretized version of it we know for the probability current from Schrödinger theory, of course. And once you find a pattern of non-trivial expectation values of such bond currents, you may claim to have a loop current state. Now, not all loop current states are allowed. There are certain constraints. Felix Bloch showed in 1933 that there cannot be a macroscopic current flowing through the volume of a system in a purely electronic system. This has certain constraints on the allowed bond current pattern. And of course, in Heidelberg, not far from Karlsruhe, there was a gentleman named Kirchhoff, and he told us that, well, in any electrical circuit, there should be the same number of current flowing in and out every node. And if I, for example, was so foolish and changed the direction, say, of one of those currents, then clearly this is not an allowed state, and the underlying loop current pattern is not a legal one. So sometimes it's actually smarter, instead of thinking about loop currents, to think about the associated fluxes, because they will always guarantee you all these constraints to be obeyed. But we will be looking at loop current pictures. Now, these states of order have a history, and have been discussed over the years in a different set of contexts. Probably one of the earlier ones is the Haldane model, where a quantum Hall effect without applying an external magnetic field, but due to the time reversal symmetry breaking of such loop current states was introduced and has been greatly influential in shaping our understanding of topologically non-trivial systems. Chandravarma proposed, and this we will be discussing a little bit more, loop current states as indicated here as a potentially ordered state in the high temperature superconductors, the Cuprates. There is a proposed ordered state in twisted bilayer graphene at a sufficiently small twist angle, which goes under the name of the Kramers intervalley coherent insulating state, which is also a loop current state. And finally, there's an intense discussion going on currently about such a state being prevalent in the Kagome metals that will also be part of this talk. So I will be discussing these two systems. So this is just a different, maybe more realistic picture of what I've sketched you with these four lattice sites earlier. This would be a charge site order, this would be charge bond order on, for example, a Kagome lattice, and this would be a potential loop current state. And as you can see, these states can not only, for example, in this case, break time reversal symmetry or certain orientational symmetries, but they also break translation symmetries. As you can see here, the flux direction or the loop current direction oscillates counterclockwise and clockwise at neighboring hexagonal plaquettes, and therefore the translation symmetry is broken in these systems. This would be a charge bond ordered state that translation symmetry is broken. It will be incredibly important for what we discuss in this talk of whether or not a loop current state does not or does break translation invariance. I'm showing you here two legal patterns in the sense of Kirchhoff and Bloch, two legal loop current pattern on a Kagome lattice, and in this case we see the translation invariance is perfectly preserved, while in that case it is not. For what we want to discuss, namely the importance of such pattern for superconductivity, the fact of whether or not these states do break translation invariance will be incredibly important. Good. So what are we going to do? Intellectually, what we will be doing is very, very simple. We will want to answer a what-if question. We want to answer if there are loop current fluctuations, what are the implications for superconductivity? And the way we do this is that we are considering a collective bosonic mode that is basically made up of finite in space in range and finite in time pattern of this type, so not even long-range ordered ones, but just local patches that fluctuate in time or space. And those fluctuating objects will give rise to an effective interaction between electrons and the vertex that is basically responsible for how electrons communicate with such objects will tell us whether or not such an interaction can or cannot give rise to superconductivity. That's all what we want to answer. So the main conclusion that we draw is that in Cuprates, where the proposal was that these loop currents are translation preserving, we cannot find any sensible scenario where they are responsible for superconductivity. Now that's a bummer, and therefore it is not really all that much fun to talk about these things, and therefore it was much more fun to look at the Kagome metals, where we found, I think that there is a very sensible scenario that explains certain important aspects of the phase diagram of these systems, and that is rooted in loop current fluctuations as well. But in this case, in translation symmetry breaking ones. I should also say what we will not do and what we will do in this talk, just to avoid any confusion. We will not derive loop currents from any microscopic model. There is wonderful work, I give a few references later, there's wonderful work done along those lines, where people try to find microscopic Hamiltonians and in the end derive certain loop current patterns. We will be much more agnostic about this and assume they exist and check what the consequences are. So we just evaluate, suppose there is a loop current, what are the consequences? And as I already mentioned, we will not really look at long-range ordered states, but look at fluctuations. The reason being, in large parts of the phase diagram of both of these materials which I'm looking at, there is actually good reason to believe that there are at best fluctuations, A, and B, it's simpler. Because once you break translation invariance in a system, you may have a reorganization of your Fermi surface, downfolding effects. You need to think very carefully what happens, and you will be depending so much more on details that you can make less rigorous statements, something we wanted to avoid. How do we do this? As I said, we have some loop current pattern here now in momentum space, and this will communicate with some collective bosonic mode that transforms exactly the same as the loop current does. And we will then assume certain correlation functions for this object, a length scale, and if you wish, so a time scale that in the weak coupling limit that we will pursue here won't even be all that important. Important is that we need to know how this loop current looks like, and this will be basically just a bilinear of fermion creation and annihilation operators with all the orbitals in whatever unit cell you wish to discuss, and there will be a matrix here that tells us how this object is behaving, what is in fact a loop current. This will of course be odd under time reversal and can or cannot break translation, can or cannot break inversion, and so forth. And once we have established how this form factor here behaves, we can proceed. And but I want to first give you a little example how to get those form factors. Here, this is an example where we have, say, 4 oxygen orbitals that are here surrounding presumably a copper site, but that's not even important for this specific example. These are px and py orbitals. The plus and minus signs are differently colored here because of the different orientation. If these px are both point in the same direction, these py and both in the same direction, then you see here there's a blue with a blue and there's a blue with a brown that talks, and therefore there's a different sign in the hopping elements. So this is a natural pattern you would find in this arrangement. If you know flux attach, put a flux in this to describe basically this loop current, which you can do with a generic vector potential. Each of these steps gets exactly 1/4 of the total flux accumulated. And then you will find that you hop from 1 to 2, from 2 to 3, from 3 to 4, 4 to 1. This gives you these matrix elements in this 4 times 4 matrix, and these different signs here are just the different hopping elements here. So it's not all that complicated, but you can see that you can make arbitrarily many sign mistakes in this analysis. Hence, what you need are smart young people in Mathematica, and this combination will resolve this problem, and then you can identify all these possible loop current patterns that you can find and come up with in a generic system. Very good. So now once we have establish this form factor, we obtain this effective interaction that I mentioned earlier that corresponds of the correlation function of our collective boson and physics that knows about these form factors. So let's go over this in some detail. The correlation function may be characterized by an ordering vector around which the system may or may not condense. This signals to us whether these loop currents do or do not break translation invariance once they condense. Then there's a characteristic length scale involved in the system. In some cases this could be of the order of just a few lattice constant. If you were to be at a loop current quantum critical point, that would be diverging, and so forth, and you assume certain scaling behavior. And very important for our consideration is just how these form factors communicate with the Bloch states that make up the Fermi surface, and that tells us basically how the system couples. Very simple. Everything is essentially simple solid state physics. The time reversal behavior of the boson, which in our case is definitely -1 because it's a loop current, determines the prefactor here, and when we go into a pairing channel, this will be essential and crucial, of course, for what is to come. And then we do something even simpler. We say, well, look, all we really want to know is what's the symmetry of the ordered state. So let's not do all this nonsense that people do by writing down strong coupling, superconducting field theories without quasi-particles and go into holographic spaces and all this stuff. No, let's be simple-minded and look at the weak coupling BCS theory mediated by this pairing interaction. And this gives us an eigenvector, and the eigenvector tells us how the superconductivity in the system depends on orbital degrees of freedom, how it depends on momentum. Is this an S wave, a P wave, a singlet, a triplet, and so forth. And the hope and optimism is that we say, well, we of course need to do a better job to go beyond this weak coupling picture, but presumably this will just describe said superconductor better, but not really change qualitatively which superconducting symmetry we would be getting. To give you an example, you look at the Cuprates, and even if you commit many, many crimes, you get a D wave. And then you need to deal with those crimes, and then you get a better description of that D wave, but it stays a D wave. This is a bit more subtle, maybe in multi-orbital systems, where there are multiple states that compete. Still, we want to see what are the dominant pairing channels in that system. Good. So everything is well defined now. There is something that I will not do, and maybe give you a little table that's easier to look at. So there are, we will talk about material-specific properties. But under certain conditions, and that's something, it's a 2 times 2 table, so therefore it's easy to memorize. Under certain conditions, you can make completely model-independent statements. And they are, of course, rather restrictive. So if, for example, our loop current state preserves translation invariance, that's very important. And if we ignore spin magnetism, which we have been so far consistently, and we can discuss what happens once we don't. And finally, if the correlation length of that system is very, very large, meaning the pairing interaction really only wants to have forward scattering at very small momentum transfers. Under these 3 conditions, we know the answer already. Namely, for every boson that you can come up with, and it depends basically only what the parity of the system is and what time reversal symmetry tells us. If this boson is even under parity in time reversal, and the famous example are nematic fluctuations, worked out here in this paper by Lederer, Schattner, Burke, and Kivelson. In this case, this boson will give us strong pairing. Nematic fluctuations are good for superconductivity. They tend to give us S-wave superconductivity, but there can be runner-ups that are very close in energy that can be unconventional, and then you can come up with arguments why even the second leading channel may even, under certain circumstances, win if somebody else helps. Nematic fluctuations are good. Then we can break inversion, for example. This would be a ferroelectric fluctuation, but one without spin-orbit interaction. We had a wonderful talk. What happens when you include spin-orbit interaction? Then things change. But if you don't have spin-orbit interaction, at best you can expect weak pairing, that in the sense that this boson is as good as any other vegetable that is around there. The proximity to the quantum critical point does not help you. Finally, the same is true if you have a time reversal odd even parity state. That would be a loop current state that is even under parity. It's also a lousy pairing channel, but at least it gives you something. And then the absolute winner is when you break time reversal and parity, and then you cannot get any pairing whatsoever. Assuming that the states that are paired are k and minus k in the Cooper pair. That's maybe something I should have added to this list here. So to give us a picture, if I have one quantum critical point here, I'm approaching it, my nematic fluctuations would want to pair, and then I would have to do a better theory than weak coupling. Loop currents of ferroelectric fluctuations would at best survive, and the time reversal odd parity states would be repulsive in all pairing channels. These statements can be made completely generally, which is why it's rather cute and worthwhile memorizing. There's an interesting implication of all of this, namely if you happen to have a photon or 2, and you want to shine it onto a piece of metal, and you want to identify whether this state becomes a superconductor, it could, but not in the sense that it causes pairing in the pairing glue photon. So this is odd under parity and odd under time reversal. And of course, photons can cause superconductivity, but only in so-called pair density wave states where it's not k and minus k that pair. Good. So that's just, I felt this is a cute table to memorize. Now we talk about cuprates. Same monastery, same floor, but it's now a square lattice. And these are states of loop currents that were discussed early on in the context of cuprate physics by Chandravarma and collaborators, and he made 3 statements. A, these loop currents could be responsible for the pseudogap state of these materials. B, their fluctuations in the normal state give rise to omega T scaling and explain the marginal Fermi liquid behavior. And C, they give rise to unconventional pairing, and in particular to dx squared minus y squared superconductivity, the state that we know to be the right pairing state in the cuprates. I will only comment on this last issue, have nothing to say about these two. The state that was proposed is this state here. It is odd under time reversal, it is odd under inversion, and it does not break translation invariance. So I don't even need to continue, because we know already it falls in the class of the really, really bad ones. But we will need to keep on going, because Chandra had a very interesting point to make. He said the quantum fluctuations of the state can be basically induced by what could be the conjugate momentum, so the angular momentum that flips and rotates things, which is essentially this loop current state. And his idea was maybe this could cause superconductivity that is even under parity, and therefore it's worthwhile looking into it. So there are arguments in the experimental investigation of these systems that favor and that don't favor loop currents. I'm not going to get into this. I have nothing to say except that this is a not yet settled situation. The argument in favor and against loop currents from the numerical investigation of Hubbard models, I have nothing else to say to this, but this is not a settled issue. Good. We will describe the system using 3D x squared minus y squared copper orbitals and 2px and 2py orbitals with some reasonable parameters. We have scanned the entire parameter space that was proposed over the 30 years of cuprate physics by the community. What I'm saying here is rather representative to all possibly conceivable parameters and indeed rather general. So those are the loop current states that you come up with. They have already been pointed out in these papers. We analyzed them and so forth, of which two are even parity states, and then there's this famous odd parity state. Let's go over them quickly. This is, as you can see, a loop current state that gives us a finite moment, orbital moment in the center. It's an orbital ferromagnet that couples to a magnetic field. It happens to also be the conjugate momentum of these odd parity states, as I already mentioned. This state is something that we now have to call an orbital outer magnet, because if you rotate this thing by 45 degrees and flip the direction of the arrows, it maps onto itself, hence it is an outer magnet, just not in the spin, but in the orbital channel. It will not couple to an external magnetic field unless you apply strain, and that we have seen in multiple wonderful talks by Ian and by Elena during this week already. Finally, you can look at these odd parity states. This would, I believe, be called a toroidal moment, and it would have a coupling to a magnetic field in the presence of an electrical field that is orthogonal to it. You could also maybe send a current because it's a metallic system. This is how you could be communicating with this ordered state. That's the state proposed for the cuprates. Here are our results. I mean, the procedure is clear, right? We have these objects. We calculate whatever the i's and the minus i's in our matrix gamma. We plug this into a linearized gap equation. We look what comes out. So I don't need to give you all the details on this one. I've done already. We find for this state dxy pairing, dx squared minus y squared pairing, and extended S-wave pairing if we are far away from the quantum critical point. So the good news is they all give rise to interesting superconductivity. These loop current fluctuations can cause superconductivity. If we go close to the quantum critical point, of course, what we said earlier is true. Namely, this guy is strongly repulsive. These guys basically stay the same as they were. So the sad news is this is the only one that gives us dx squared minus y squared pairing, which is, however, a rather weak instability, not amplified by the vicinity to the critical point. There would be no superconducting dome at where the critical point would be or is expected to be. And it also has never been discussed in the context of cuprates. This has been discussed and was argued to give us dx squared minus y squared superconductivity. We find that it doesn't. It gives us dxy, and this way does not give any superconductivity. So here, this is the sad news of the day. Loop current fluctuations cannot describe the superconductivity in the cuprates, unless we think about states that break translation invariance. I'm not going to get into this here right now, because we will now look at the Kagome systems and see how translation invariance rescues the system. Good. So this is the summary for the cuprates. Now the Kagomes. Now we will look at finite Q momentum states. those that break translation symmetry. There was already quite a bit of discussion on those systems, therefore I can be brief. This is the vanadium sites are indicated here in red. The antimony sites, the in plane and out of plane. These are the out of plane. The in plane is hidden here under the alkali metal system. These systems are charge density wave, form charge density waves, and at low temperatures become superconducting. They have a rich phase diagram as function of pressure or as function of hole doping, where you can suppress rather easily the charge density waves, while superconductivity seems to be surviving for quite a bit longer. And this is here the Kagome basics, something that was pointed out long ago. In the literature, if you look at these 3 vanadium sites in the unit cell here, red, blue, and green, they have the interesting property, and I believe Abai had already pointed this out earlier during the week. No, not Abai, Eduardo. Sorry, one of those SDM guys, right? So, this is all reported, right? Anyway, Eduardo pointed out very clearly that the orbital weight that you can find on the Fermi surface that is indicated here, and there are these Van 't Hooft singularities of what goes under the name of M points, these points here, this is dominated by sites in each of these 2 triangles. So this state here, these states here are dominated by that vanadium site, the blue ones by the blue site, the green ones by the green sites, which already tells you if I'm coupling this point to that one, so this point to that one, I will basically couple in real space bonds, red to green, right? And therefore, this is the charge density wave character of these systems is of bond character, not of site accumulating character. I think that's the easiest way to understand that. So we will not use this simplified model that is underlying this here single band model on 3 vanadium sites per unit cell, but we realized the hard way that one has to pay attention to the details of the electronic structure of the system and included in the end 30 different orbitals, in plane and out of plane antimony and the d orbital on vanadium to describe the band structure. The loop currents will then be formed out of a subset of those, namely the 13 orbitals that are odd under a mirror symmetry in the xy plane. This is the resulting Fermi surface. The key new addition is this additional antimony band here in the center of the Brouillon zone that you can see also dispersing here. And important is you get a much richer structure near these M points with multiple Van 't Hooft singularities, as you can see here. In total, there are 3. 2 of them are relevant to us because they're made of these odd under mirror symmetry forming orbitals. Very good. What I just said, namely that you can translate real space pictures into momentum space pictures, survives even in this more realistic model. So these are the sites on the red vanadium sites, the blue and the green ones, and this band in the middle here is essentially then also made up out of these and in-plane antimony orbitals. Very well. This is the superconducting gap that you can find. It's been measured by SDM measurements. We see a well-established superconducting, fully established superconducting gap. To me, this looks not like this was, say, a dx squared minus y squared superconductor. This is a fully gapped state. Right? So any theory that if our analysis of loop currents gives us something that does not have a fully established gap, then probably we are not having the right theory. In addition, the muon spin relaxation experiment see that even in systems where there's no loop current induced potential time reversal symmetry breaking, at the superconducting transition temperature, in some of these data this is the case, there is a change in the relaxation time, so there's indication of potential time reversal symmetry breaking in the superconducting state. One has to be careful with this. In the past we had seen examples, in particular in the context of strontium rusinate, where, for example, this is only an indication of competing channels, closely competing channels that then mix, for example, in the vicinity of defects where the symmetry is lowered and can break time reversal symmetry. One has to be a bit careful with the interpretation of these results. But at least, if you only have one winner, it's not easy to explain these data. You want to have multiple competing superconducting states, or maybe one that breaks time reversal symmetry breaks time reversal symmetry. Now these are key observations here. These are this is the superconducting transition temperature under pressure. I told you the charge density wave disappears quickly at about a gigapascal or so, or 2, or half in this system. But if you pressurize even further at around 8 to 10 gigapascal, the superconductivity disappears. This is the case for the cesium vanadium antimony, but also for the potassium. You see the superconductivity disappears. But then, and that's interesting, once you pressurize further, you have a reappearance of superconductivity. Now this could be interpreted as a little dip in the superconducting transition temperature, and the red and the blue is just to misguide our perspective on the problem. But there's something very interesting here. You can look at the upper critical field and the temperature behavior in both of these systems. Let's look at this one because the results are clearer. This is the load pressure behavior, this is the high pressure behavior. We have even a larger TC here compared to the high pressure system that's been plotted here, but the upper critical field of the lower TC values is a lot larger compared to what we see here. Something very similar, but here you need a bit of an extrapolating eye, was also being seen in the cesium data, but those were published first, I believe. This is from Hefei, this is from Hangzhou. Important is, in my view, these are different superconducting states because they show a very different behavior of the upper critical field. So the assignment now for theory is to find fully gapped state at ambient pressure and have at least something to say about competing states or the possibility of multiple pressure-dependent different superconducting states. Excuse me? I don't even know what it is. They see some kink in transport behavior, but I don't think anybody knows what it is. Raphael, do you have something to say? No? Okay. Okay, good. Now, the experimentalist of this paper already pointed out what could be the reason, namely band structure calculation, showed us that this antimony band here disappears near this pressure of about 10 gigapascal. So therefore we have a Lifshitz transition where we have or do not have the antimony band involved. Right? So the statement here is, if you lose the antimony band, that's bad for superconductivity, but it's not all that bad. Right? So this is kind of the upshot of this story. Good. There are SDM data that see a magnetic field direction dependence of the intensity of the Bragg peaks related to this charge density wave that's been interpreted as having a chiral character or interpreted as being evidence for at least field-induced loop current states. You see this by several groups here. There is a very, very interesting experiment from the Philip Moll group where they see at least strong evidence for magnetic field-induced mirror symmetry breaking in the system, which could also be very consistent with these loop current states. And there are NMR data where we see a magnetic field direction dependence of the relaxation rate in the system that is most naturally be interpreted as having orbital direction dependent fluctuations in the system. So there is, if you want so, let me just write it like this, there's some evidence that there are translation symmetry breaking either field induced or even zero field existing loop currents in the system. There's no smoking gun experiment to this day as far as I understand it. This is what I quickly jumped over, is just a list to give proper credit to the work where loop current states have been derived from microscopic models. Usually you need some further range Hubbard interactions. This work here by the Toronto group is particularly interesting because they found out that if you include all these multiple Van Hoof singularities, then you only need nearest neighbor Coulomb repulsion, which is, I think, very realistic. And then this is, of course, all this important work or a subset of it that classified loop current states and so forth in these systems. So here, this is a typical picture of a loop current state. I showed it to you already, that break translation invariant in the proper way. But of course, we have in these systems 3 different ordering vectors. The ones that are important are believed to be the ones that connect these Van Hoof points. And of course, we can draw the pattern for all 3 of them. They're just rotated by 120 degrees relative to each other. In reality, this will be a superposition of these 3, sorry. But this would be the natural basis states that would describe the system. Here, the loop currents flow from a vanadium to a vanadium to a vanadium to a vanadium and so forth. We felt we should pay attention also to the antimony, simply because of the fact that superconductivity disappears when the antimony disappears. So we thought, okay, why couldn't we also have other loop currents, for example, those that go from the vanadium to the antimony, to the vanadium to the antimony? And then you might think, well, this antimony is maybe not all that interesting. How does it efficiently couple to this? And this is actually very interesting, simple kinematics. The antimony sits here near the gamma point. These are the important momentum points. So if I connect this gamma point in this direction by Q3, the important transferred momentum that describes these modulations, I'm ending up at an endpoint. This is where all the music plays. So actually, these states couple strongly to these Van Hoff states, and therefore these loop current states should not be ignored, just kinematically in the system. And here we have done this. So there's another loop current state. So I'm giving you here all of them. These are two different basis states that transform identically, and this is one that goes over the antimony, and that just requires a little bit of analysis to come up with all of them. I need to stare for very long at these pictures to make any sense out of them, but in the end of the day, this is all kosher. I believe in the end of the day there will be some superposition of these states that makes up the loop current in this irreducible representation that we looked at here. Good. This is an odd parity state, and well, I don't think I need to go into this. Here are the results. Again, if the loop current states that traverse also to the antimony are important, basically we get a strong coupling between the M point and the gamma point, because that's what we've just discussed. This is an electronic pairing mechanism. It has to change the sign of the pairing wave function. Otherwise it wouldn't work. So what we get is what you would expect. We get an S plus minus space. So we have we have a band here at the gamma point that has one sign, and then we have all these vanadium dominated states out of here. They have the opposite sign. And this state is actually not even relevant whether we have this shown even parity or odd parity state. They all give us very robust S plus minus pairing in the system. That happens to be, everything taken equal, to be the most dominant pairing state we find. However, we can also we find the second winner, namely, which would be something that is predominantly made only out of those outer vanadium sides, and there's a two-dimensional irrep with degenerate dx squared times y squared and dxy pairing. This degeneracy is important because, as we could show, that their natural superposition is in a way that is time reversal symmetry breaking, and therefore the superconducting gap is the square of this plus the square of that, and you will again get a fully gapped state, albeit a state that has some anisotropy. If you carefully look into the system, there are some accidental nodes. Accidental node is one component in a regime where the other one may be small, so therefore there should be some anisotropy in the superconducting gap. So those are the two winners. Everybody else is irrelevant. So we can look at this, and as function of the position of this antimony band that we can tune, something that's been accomplished by changing pressure in the sample, then we find the winner is the S plus minus state, which we believe to be the right state at ambient pressure. Once we increase the pressure, this state is essentially staying here, staying put. We then have the Lifshitz transition, the superconducting state dies, and then the second winner should take over and is a dx plus d plus id superconducting state. So this is our expected phase diagram at the Lifshitz transition. We go from an S plus minus state to a d plus id state. This is going to be in our view, the ambient pressure superconducting state. At high pressure, we would expect this state. It is very hard to make measurements under very high pressure, but with hole doping and a combination of strain I've learned recently, one can indeed move this gamma band away from the Fermi energy, and that's an interesting experiment to do, and we have certain predictions then what should happen. There's an implication if you just look at this HC2 curves, the characteristic velocities of this antimony and the vanadium bands are very different. So if I just estimate HC2 as the flux quantum, the critical transition temperature, and the typical velocities, in this high pressure phase I have much smaller velocities because all I have are these flat bands around here. So smaller velocity gives me much larger HC2, while in this phase I have these much faster antimony bands, and therefore I get a much smaller HC2. So therefore this is at least phenomenologically consistent with this picture, that we would get this different behavior of the upper critical fields. I can conclude. For the cuprates, we said that loop current states that were proposed, namely the ones that do not break translation invariance, are no efficient pairing glue under no circumstance that we could come up with. This may change if they do break translation invariance, and we even looked into this. We found that there are regimes where this could happen and work, but not if they don't break translation invariance. For the Kagome system, the situation looks like this. It could always be that the Kagome systems are just electron-phonon superconductors. I find electron-phonon superconductivity a very respectable mechanism. We should not always ignore it. But there's some indication that the pairing is unconventional, time reversal symmetry breaking in some character, that there are different pairing states, and that there are competing pairing states even at ambient pressure. For this, we have a story that at least makes sense and goes back to the only collective mode in the system that has any chance to give us a non-S-wave superconductor. Thank you so much for your attention.
Yeah, very interesting. So is there a way to understand then, just looking at the gap equation, the repulsive part, why does the proximity to the critical point suppresses? Like, what happens to the kernel that sort of works away and
in the odd parity, odd time reversal symmetries, non-time reversal preserving state?
Yeah, what's the difference between the orange and green?
So basically, I think one can even understand this. So you have a gap equation that sits at a given momentum. You have a pairing interaction, whatever there is, some pairing interaction. There is whatever, some stuff that gives us a log. If I have time reversal odd, then this matrix element here is positive. It's negative definite in the convention I just used. So let's write it in the usual way, right? If this is attractive, then you have a minus sign, then it's good. If your time reversal odd, there's this different coefficient up front, and therefore time reversal odd is not good. Now, you cannot easily see a solution. The usual way out, of course, if this guy here is repulsive, is that on your Fermi surface, you have a large momentum transfer where your gap has one sign here and one sign here, and you have a large momentum transfer. That is how we understand rationalized D-wave superconductivity. But if you have no translation invariance system and you're going to the critical point, this is dominated by Q goes to 0 states. So therefore, you can only scatter a state with itself, but you cannot change the sign of itself. The only quantity A equals minus A that we know of happens to be 0. So therefore, then if you have parity equals -1, this quantity in this limit for k goes to k prime small momentum transfer is finite. The good news only is if you have a parity that is +1, v of k minus k prime goes like k minus k prime squared. So it actually vanishes where the correlation function is supposed to diverge. And therefore, the forward scattering is as good as any other momentum state, and therefore you don't have that problem. And this is a consequence of just taking matrix elements in a system that has no spin-orbit interaction. That's important. And then you see it just on the Fermi surface, matrix element is 0. That's the entire story.
Hi, Jörg. Thank you for your talk. So for the Kagome materials, there have been proposals of also spin fluctuation driven superconductivity by the group of Tomale too.
Mm-hmm.
So my question is, how do the loop current either relate or perhaps compete with the spin fluctuations for the pairing mechanism in this system?
So I think spin fluctuations is a very viable scenario if there are spin fluctuations. And the problem is that there is no indication for the presence of such fluctuations in these systems, while there are indications that the loop current fluctuations are there. So if you have a system with spin fluctuations and loop current fluctuations, my gut feeling tells me the spin fluctuations would be the stronger ones in their pairing source. It's just accumulation of, say, historical knowledge rather than an analytic calculation or so. But I don't think there's any indication that there are, in fact, spin fluctuations in that system. If they are there, they could be clearly competing state. So far, I think we have some rather convincing evidence that they are not there. Yeah.
So I'm trying to think if these loop currents can actually cause, like, say, I can associate this to some internal magnetic fields.
Yes, I would.
Okay.
Once they order.
Okay.
In our case, we're always in the fluctuating regime.
Okay.
But once they order, they would, yes.
Can we have an idea if they, I mean, I try to think of experiments, right? So could they be large enough to cause, like, say, absorption dichroism in XMCD experiments?
Absolutely. So there is dichroism measurements. But dichroism measures typically mirror symmetry breakings. And there are experiments where essentially dichroism was observed by ARPES. It's a group in Mainz and in Frankfurt. They have, and in Karlsruhe. And they have seen this dichroism in ARPES. If I talk to them, they tell me just chirality does not give us the size of the signal that we are seeing here. That's a quantitative statement, but it's a statement. What you then you would have, well, why don't I just make a Kerr effect measurement? That's an interesting statement as well. The problem is this by itself is not, I mean, Raphael should answer this because he has thought about this a lot deeper than I did, and actually he should, but the state itself, because of the staggered nature, is not a ferromagnet, if you wish so, but an anti-ferromagnet. Now then life becomes even more complicated because you couple to the charge density waves that essentially makes this a pseudo-ferromagnet again, because you don't break an additional translation variance, right? Or in other words, you couple to the charge density wave modes to absorb the momentum. Under strain, I believe the prediction is there should be a Kerr effect. It hasn't been seen. Without strain, I'm very chill that it shouldn't be seen, I think, at least for some of the loop current states. For the one that you propose, there should not be a Kerr effect, if I understand correctly. Yeah, he should answer this.
I think it's pretty clear that there's no net orbital magnetic moment. So whatever configuration you have, it has to be compensated. So Kerr or what's the other one? The relative of the Kerr.
Faraday.
Yeah, exactly. They're not going to see anything, and they haven't. Now, some people have proposed a state based on the STM data that is actually the equivalent of an orbital altermagnetism, like piezomagnet. So you apply magnetic field, it distorts. There are other possibilities. Jörg just mentioned one where you actually have essentially the equivalent of an orbital anti-ferromagnet as well. The tricky part is that in the hexagonal lattice, when you have more than one direction of loop current, it necessarily induces charge density wave. So it's hard to separate. You can't really separate, and that comes from some anharmonic term. So there's a lot of research in this area, and I think nobody can say for sure that there isn't. And I completely agree with Jörg that if it's not there, it's getting there. It's close, it's nearby.
So this gives us plausible, the fact that we are never actually going into the ordered states gives us what goes in the legal term of plausible deniability, because even if it's not there, we only need it to fluctuate and to be a nearby state that you can, for example, easily field induce. But that's just theory language, right, for trying to get away with problems. Yeah.
Okay, more questions?
Is this Lifshitz transition first or second order?
The Lifshitz transition itself, the first order transition, but the superconducting transition that is happening there, in my view, should be first order in a clean system. But
So
the Lifshitz transition itself, in the absence of superconductivity, is just a second order.
nice, just
yeah.
and this one.
Yeah. So if there was no
so the
superconductivity,
Fermi changes smoothly.
it's just smooth. It's just a Fermi surface that shrinks to a point and disappears. Very simple. It's just a
Okay, so that's the
yeah.
simple one.
That's a very simple Lifshitz transition. The superconductivity in a 2D system should have, in my view, a first order transition. That because TC does not have to change
Yes.
from both sides continuously. So it could be that there's a tetracritical point that is in principle an option, but my suspicion is it's a first order transition.
And have you thought of any experimental way to verify this?
Well, we've seen the experiments, right? They don't see what we. I mean, first of all, this. I need to go back. Yeah. That's what the experiment sees. It could be that this is a disorder effect. It could be that superconductivity is just very weak and then strongly affected by disorder in the regime where it's just small, right? You have an underlying disorder, you would always get rid of the superconductivity. In the clean system, I would expect there to be a first order transition. In a disordered system, pair breaking would typically suppress pair breaking when the TC is just getting too weak. So that is my interpretation for this behavior, but be my guest if you have a better interpretation, yeah.
Okay, actually, I have a more general question.
Yes, please.
I want to take the opportunity because just before your talk, a master student of mine asked me a question, and I probably gave the wrong answer. So I want to check now the answer. So I told him that if I have like two domes,
Yeah.
I would always expect that these superconducting phases are somehow different. And when you're giving your talk,
Yeah.
you said that you think that they should be different. So it's not like a necessity. So what would be the rationale for having a double dome, but the superconducting phase are kind of the same? Because as I said, I would expect them to be different.
Yeah, I think there are many, many different scenarios we can go through.
Where
There's
they
no
could
clear
be the
answer to
same.
this. I could have,
Okay.
for whatever reason, a pairing interaction just happens to be weak for some. It just runs out of steam on occasion because it's just, have to climb some stairs. So then what you would get is, with a little bit of disorder, you would get two separate domes. Right? With no disorder, of course, that should be one phase, but you could, in experimental situations, see two separate domes of identical superconducting states. That is never illegal, right? It would be unkind if this were to happen because it would mislead us on occasion, but it's not illegal. Here, my argument was this could be different because of this different magnetic field behavior. It's quantitative, and if you know the symmetry, you know for sure whether they're different or not, right? But we don't at the moment. But there's no clear answer to this question. Yeah, yeah. They could, in principle, I just gave you an example by which they could. So you didn't, whatever you answered, you didn't give the wrong answer. So. Yes.
I just wanted to follow up on the question
Yes.
of comparison to experiment, and now that the slide is up.
Absolutely.
The left-hand side, it looks like the two superconducting domes could also just be entirely disconnected, right?
They could, yes.
So in which sense is that consistent with the idea of sort of a
It would have
first-order-
different degrees of disorder, would be my argument.
Okay. And TC go, I mean, here, also in both cases, it looks like that the critical temperature right at the transition
Yes.
between the two superconducting phases is 0. In
That's
your
how it looks like, yes.
in your plot it looked more finite.
Yeah,
but
I mean, we could have, I mean, first
but
of
you-
all, our plot was just something that we
Theory,
drew
yes.
because we drew it, not because we calculated it.
of course.
Why did we draw something that doesn't look like the experiment? Because what we drawn is what our theory would absolutely naturally give for the clean system. And this, I don't think it would be legal to draw anything else, right? So therefore, yes, this doesn't look precisely like the experiment. It doesn't really make me all that nervous. I mean, for
over.
reasons that, I mean, disorder can distort these phase diagrams so easily.
Okay, thanks.
Quick question.
Yeah.
The D plus ID breaks time reversal.
Correct.
So I suppose it would induce loop current order linearly.
It would.
I don't know if it's easy to
yes.
distinguish them, but
Yes. Mhm.
I think
So- yeah.
symmetry-based arguments would say that
Right.
they would.
So you have broken time reversal symmetry. Now the superconducting order parameter will couple to this, but one has to keep in mind one has, in the Ginzburg-Landau language, I need to have a gauge invariant coupling, and I have to preserve momentum to translation invariance. So it's not quite it's not a bilinear coupling. By all means, it can't be. But they will certainly communicate with one another, for example, with the help of a charge density wave and maybe an S-wave superconductor or something. But it's not so easy to have them talk to one another. Yeah.
So you mentioned twisted Bailey graphene at the beginning of the talk. So could you please comment what would be the picture for loop current fluctuations there?
In which system?
Twisted bilayer graphene.
Well, this is a time reversal symmetry breaking state that in this specific case breaks inversion also in time reversal. And you would have to measure these loop currents by, it is translation symmetry preserving in the more rake context. So therefore you should see a Kerr effect in that system. So it's a bit subtle because even though it's translation is symmetry preserving, many of these loop currents in the Moore racer will actually cancel. But they don't actually all have to cancel. So it's not going to be, what would be more interesting is if you could make a local measurement on the scale of the carbon atom distance size to be, for example, you want to, so we are in discussion with, in the Kagome context with SDM groups where you place magnetic ions on top of this and see how they couple to the loop currents. That could be a way to do this, but it's not easy.
Hi, Jörg.
Yeah, hi.
I know that's something that you chose not to do. So, but could you still maybe give more details on which are the possible microscopic interactions that would give rise to the loop current?
Yeah. Mm-hmm. So again, the model that I studied personally in most detail is the one that was proposed by Youngbaek Kingham and Hye-Young Ki in Toronto and their collaborators. They pointed out that if you have two Van Hoff singularities that have opposite behavior under a mirror symmetry operation, and if you have nearest neighbor Coulomb repulsion, this can conspire, this gives you an attractive interaction in precisely the loop current state that we have been discussing here. So typically, and this was also what was discussed in the cuprate context, it was already understood by Chandra that you need to have not the local Hubbard repulsion, but at least the nearest neighbor Hubbard repulsion in order to move these currents around and have instabilities in these channels. Raphael wants to comment on this one, but maybe before I let him do this, formally you can even show that relativistic effects where you couple to phonons would give rise to, are attractive in the loop current channel, but these are extremely small effects unless you have strong spin-orbit interaction in the system.
Actually, is a follow-up question. My recollection, I mean, for the Emery model, for the cuprates,
yeah,
that there's no parameter regime where you can find the loop current as the leading instability.
Unless you take apical oxygens into account.
Okay.
Yeah.
But
yeah.
I'm not sure for the Kagome anyone has done a careful job to see that even, maybe that's my question. Do you know if they did to show that this is actually leading instability and not just a instability? Like all these RG calculations say, oh, it's possible.
Yeah.
but not as like the leading stability. So I don't know if you.
So the Toronto group compared it and showed that it is dominant over the charge density wave instability, but not to spin. They have not done this. And the easiest is to do one of those FRG calculations or something. Yeah, I'm not going to do this. I'm from Germany, so I'm not allowed to do FRG. So, yeah.
So, is there a characteristic frequency or velocity for these loop currents?
Yeah, very good. That's a very good question. So, if you look at the NMR data, this is really the only indication that I know of where we have some dynamical information. And if I look at the slope of the spin lattice relaxation rate, and use numbers for the hyperfine couplings and dipole couplings that is known, then what you find is something of, say, 5 millivolts or so. 5 to 10 millivolts. Or there's some H bar and something like this. Yeah.
Okay, so let's thank Professor
Thank you so much.
Schmalian.